Okay, this video is on the properties of light. So, light is an electromagnetic wave. It's a small band of electromagnetic waves that are at a certain frequency that make up visible light, what we can see. And so, when we look at an electromagnetic wave, the way you're going to create them is you can have these moving charges of currents create a magnetic field, and then an oscillating magnetic field create electric waves. That will create an electromagnetic wave. Now, what's kind of fun about electromagnetic waves, as complicated as it sounds like what starts one, what's kind of fun about them is once they're generated, they propagate themselves. They go indefinitely, forever, just propagating themselves. They don't need they don't need anything. They can do it in outer space. They can do this in a vacuum. And if you take a look at this wave, you have an electric field, and that's this one, and it is perpendicular to the magnetic field, which is this blue one, right? So you can see these would be perpendicular to each other, 90-degree angles. And both of those are in a different way, perpendicular to the direction of travel, which would be this way. And these actually propagate in a way where the magnetic field will go, and then you'll have the electric field, and then the magnetic field, and they'll go back and forth and propagate themselves indefinitely. Okay, so you can actually do a demo. Well, we could if I had a vacuum tube, but I don't. Where you can stick something in it and you can see it, but you can't hear it. Sound requires a medium to travel through. Electromagnetic waves, including light, travel through empty space. Okay, so the measuring of the speed of light. The first thing was an astronomer noticed that one of Jupiter's moons, Io, wasn't orbiting. It had an irregular orbit, and they couldn't figure out why was the orbit irregular, why it should just be a constant orbit. And one guy kind of thought, well, maybe it's when it's really far away, it's the light that's taking the time to get here. And of course that was correct. And then later there was a guy named Michelson who wanted to measure the speed of light more accurately. And what he did was he took this rotating mirror, and this it was a large octagon of a mirror, and he actually floated it on a bed of mercury. Can't imagine having that much mercury nowadays. But he floated this on a bed of mercury over here. And this was essentially from one mountaintop to another, right? 35 kilometers. These are not close. This is one mountaintop over here, and you have another mountaintop over here. Because the speed of light is very, very quick. You're going to have to spread it out a little bit. And he had a light source here. And what he did was spun this thing. And if it spun enough for this mirror here to get here, 1/8 of a spin, then the light would make it here, bounce off the mirror here, and go right into his eye, right? But if it was a little too fast, the light would end up bouncing this way and miss his eye, and if it was a little too slow, the light would bounce this way and miss his eye. And when he got it just right, the light would bounce here. Now, of course, he had to have a basic idea of the speed of light, because you could get it one full turn off, and they were not one full turn off. He knew enough to get it within 1/8 here. But that was the first really accurate measurement of the speed of light. And here is the speed of light. We tend to just say 3 × 10⁸ meters per second, but if you want to divide it out, there it goes. And you can do calculations just like you can do on anything. It's always the speed equals the wavelength times the frequency. And since that is your basic formula, wavelength then equals speed over frequency. This is the exact same thing as we do with sound. And if you look at a radio station that has 100 megahertz as its station, then the wavelength of that would be 3 meters, right? You can do math on the speed of light, same as you can do it on the speed of sound. All right, so here we go. The very, very, very small spectrum that is visible light is right here. right here, very small spectrum that's visible light. And you have this very low spectrum down here, these long wavelengths. Okay, these are your radio waves, like for getting FM and AM radios, right? So your AM's very low. Here's your FM. Then you get to infrared, which is close to red, and then you have your visible, the Roy G. Biv, okay? And then on the other side of violet, you hit ultraviolet, and then you get to X-rays, and then last up here, you'll get to gamma rays. Down here, this is just trying to give you a scale of how big these waves are. So some waves are very, very long. These waves actually are so long, they tend to bounce off. You've probably heard this thing called line of sight, that, you know, things will go with the line of sight. That means sort of the same way that light goes, your X-rays will go, your gamma rays will go. That's actually not true when you get down to the FM and AM. This is why you can receive stuff while you're under a bridge and stuff. These actually bounce off stuff and travel through things quite efficiently, which makes them good for, you know, radios being far away. It'll actually bounce around quite a bit and get the signal where it needs to go. Okay, so we can talk about transparent and opaque materials. And when you talk about transparent and opaque materials, you need to distinguish which electromagnetic wave you're talking about. For example, I can say, is it transparent to visible light? Or is it transparent to ultraviolet light? Can you get a suntan through it? Or is it transparent to infrared? Can you feel heat through it? Usually, if you just hear transparent and opaque, we are discussing visible light, okay? Something that's transparent will allow light to pass through it, okay? And something that is opaque reflects that light. All right, so just some fun things. When we look at physics and science and we look at light, it's fun to look at the perception of distance. And this gets a little bit into art, okay? And so we're going to look at some art paintings and different ways to look at things. And so those of you who are in art class, you've all seen this before, but we'll try to hit it a little bit. Occultation is when what object in front hides what's behind it, okay? And then you have geometric perspective, which is as things get to the horizon, they look smaller and smaller and smaller. And you can actually do geometry, right, to figure out just how small they should look. There's something called atmospheric perspective, and that is what is at the horizon is always hazy and slightly bluish. So if you look at, the purple mountains, majesty, blah, 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 things that are really far away tend to get a purplish blue haze to them, and that's just from the atmosphere. And then, of course, lighting and shadows, we'll do a lab on shadows just for fun. And then stereopsis is just how we view with two eyes. We actually see three-dimensionally because we are looking through two eyes. I know it doesn't sound true, but truly, if you look through one eye for a long time, you lose your three-dimensional perspective. It works best if you do that in a place where you are not familiar with like if you do it in your own bedroom kind of thing, it doesn't work because you know where everything is. But if you go around and just cover one eye, you can lose your three-dimensional perspective, especially in a place where you're not familiar. All right, and then relative motion, and you can see this on the freeway as you're driving and you look out your window, you know that it seems like the objects near you move by very, very quickly. If you look down rows of, grapes or fields or whatever, that the ones just next to you just fly by and the ones way far away look like they're going super slowly. That's relative motion. Okay, so occlusion, here we go. This painting, you're just looking at it and you can see the child should look like it's in front of the mom. And the reason we see that instantly is because the child's blocking the mother, right? That hides the object behind them. All right, distorted occlusion. This is how we get sort of those fun paintings where the image just doesn't look quite right. There's a bunch of these. There's tons of them. And you just know something's wrong, but you can't figure out what it is. It's usually occlusion. It's usually they put something in front or behind and it shouldn't be there. All right, perspective, this just shows you the objects in the distance are smaller and follow geometric rules. And this goes directly to the horizon. That geometric rule will take you right to the horizon. All right, perspective examples. This is just a couple of slides that go in order, and it's kind of fun. You have a bunch of gazelles in the photo, appear to be about the same size, and they're just running. And of course, the ones in the back are smaller than the ones in our front, but that makes sense to our brain because things closer to us look bigger. When we mess with it, then it's kind of interesting. There's the guy way in the back, and we're going to move him to the front, and there he is, and it looks like an ant. And that doesn't make sense to our brains because to be that small, he should be way in the back. All right, now if we're going to move that guy down, you're going to get a difference as well. All right, so we're going to move the big guy to the back. See the big guy? He's going to the back. There he is. That looks ridiculous again. He's some giant, monstrous gazelle leaping down. And that is all perspective. Okay, transparent materials. Remember we're talking about opaque versus transparent. Light is transmitted similar to sound. So if you vibrate, and if the atoms and the electrons vibrate at a certain frequency that's transparent to the light frequency, it'll let the light pass through. It'll actually hit those molecules. They'll vibrate at the same frequency, bump into their neighbor. The neighbor vibrates at the same frequency, and out it pops the other side of the glass. Versus, something that's like rubber where they're not vibrating at the same frequency. The light just hits it and either gets absorbed or reflected backwards. All right, so this is their kind of goofy animation for this. But here's your piece of glass, right? Here's your piece of glass. This is glass from here to here. So we're looking at the side angle into the glass, right? Not the front of the window, but we're actually looking at a side of piece of glass, and the light's hitting it from over here. So it hits the first atom of glass, which can absorb the energy and then spit it out to its neighboring atom, which absorbs the energy here, absorbs it, and then it's going to spit it out to the neighboring atom and absorbs the energy and then spits it out the side of the glass. So really, as you look at light traveling, quote unquote, through the glass, it slows down, and we can actually measure the difference of speed. But that's not because the speed of light has slowed down. It's because it's been absorbed and then kind of regurgitated out the side and absorbed and regurgitated over and over and over again. There's more than 3 atoms in a pane of glass for the width of it, and that slows the light down. It is actually inside the glass as it jumps from atom to atom, still traveling at the speed of light. It just has to get absorbed and then spit out again. Okay, shadows. Kind of fun again, back to shadows. But shadows can tell you where the light source is and how close it is, because you can look at these 2 different flowers. When the flowers are close to the back of the wall, it's very, very clear, but when you have a large distance between the object and the shadow, they end up blurring. The shadow gets blurry. Okay? Why is that? Well, here's a ray tracing. You have a light source, and actually what's kind of fun too is, so you have this light source, and you have light that's hitting it, and it's hitting all over the place, right? We have this bright light area, and we have a bright light here, and we have light that's getting blocked by the object here. And what you end up with is a blurry shadow here called a penumbra. And a penumbra is a partial shadow. And then here you have an umbra. Think of the same word as umbrella, okay? This is the umbra, this is blocked. All right, that's a complete dark shadow, and you have a penumbra here. What's kind of fun too is that these light rays tend to bend just a little bit around. Remember, light's a wave, and as they hit the edge, they'll tend to bend in a little bit, and you'll have a little bit of this effect because light is a wave. It's not just a particle. So part of your penumbra is just the number of rays hitting it, but part of your penumbra is actually caused just ever so slightly because light is a wave. Okay, solar eclipses kind of fall into this whole shadow, umbra, penumbra thing. In a solar eclipse, because of the large size of the sun, the rays taper to provide an umbra, or a total eclipse, and a surrounding penumbra, the partial eclipse. So if you look at the eclipse, when you have the moon lunar eclipse, which is the moon directly behind the Earth. So here you go. You have the moon right here, directly behind the Earth. You can have a full lunar eclipse. If you have a solar eclipse, you need to be here, and the moon has to be between you and the sun. And so people who see this eclipse have to be in the right spot on the planet. It's a much smaller area, I guess, that actually gets to see this, is what I'm saying. Very often, the moon, because the way it goes around its orbit, it's not directly in line with the sun. It tends to wobble up and down a little bit and not be directly in line. So we don't get these every single month. Like you might think, well, we should have one every single month. It doesn't work that way. The way it wobbles in its orbit, it's fairly rare to get these. All right, polarization, polarized light. So remember the second slide where I showed you that there was a up, down, there was a perpendicular aspect. You had an electric field and a magnetic field. Well, light is polarized when its electric field oscillate in one plane, when they're all bouncing up and down. Normal light is not polarized. Normal light, the stuff's just kind of going everywhere. It's, 30 degrees, 27 degrees, 80 degrees. It's all over the place. But if you can polarize light, that means you have them all lined up, so all the electric fields are going in the same plane. They're all either up and down or they're all sideways. As long as they're all together, you have polarized light. Okay, well, you can use polarized film to force all the light that's coming through it to be in one direction. And what polarized film is, it's kind of like a grate that prevents the light that's zigzagging the wrong way. So if you look at this first one, the light's going up and down and it passes through that slit no problem. Well, now imagine if the light's going back and forth this way, it can't pass through that slit. And so what they're trying to show you here is that the light doesn't go through. It's no longer coming through. Just like a rope, if you shake it this way, will not go through a slit that's up and down. And that's how a polarized film will get rid of all the light except for the light going in the correct direction. Okay, so when you look at how much light makes it through a polarized film, how much actually goes through, there's a formula, and that's the intensity of the light is going to equal the intensity of the initial light times the cosine squared of the angle. And so the way I kind of think of this is here's your initial transmitted wave, okay? If we put a filter that's at a 45-degree angle in front of it, we can imagine losing half that light, because if it was perfectly in line, 100% of the light would go through. And if it was perfectly across it, 0 would go through, right? Nothing would make it through. So at a 45-degree angle, you can kind of imagine half of it would go through. Well, if you do the math of, cosine of the angle squared of a 45-degree angle is 0.5. So that's correct, right? Half of it should make it through, and that's what the formula tells us. All right, so here's some fun stuff. If you have a polarized film, if you have more than one, it's always fun. If you put one up and down, and you only get light that's polarized up and down, and then you put one across, no light can make it through, right? So here we have the light polarized up and down. Here we have the light polarized this way. So we've let only the waves going up and down through. Now they hit this grate. It's the wrong direction. Nothing makes it through. Okay. Sometimes you get natural polarization. This is why people wear the sunglasses that are Polaroid sunglasses at the beach and, not everywhere else. And the reason is because you will actually get polarization at the beach. There's this natural amount that will be reflected off of water that will cause that light to be polarized, and then your polarized sunglasses actually work really well in that case. Okay. this is just kind of fun, but we need to talk a little bit about radio waves. These are electromagnetic waves, and I want you to look at we're going to look at AM and FM really quick. You have what is called a carrier wave. Remember that big long one of all the electromagnetic waves. AM are sort of these really long, big wavelengths. All right, so here's your carrier wave, and really these things would be really like meters and meters apart, but here you go, here they are. And then you have a program, some kind of audio you want to embed in this carrier wave so that when it's transmitted to a radio in your car and you're driving, you can listen to the audio. Well, AM is amplitude modified. So they're going to modify the amplitude. They're going to modify this amplitude. They're going to add these two waves together, and the wave here will give the carrier wave a higher amplitude, and the one here with the lower amplitude will give the carrier wave a lower amplitude, and they literally modify the amplitude of AM. That's what AM stands for. So this is the crazy signal that comes out to your radio antenna in your car and then can play the audio or the voice or whatever you're listening to, because it is embedded in that signal. FM is going to be frequency modified, okay? So we're not going to modify the amplitude of this wave. We're going to modify the frequency. So we're going to add these two waves together. We have, again, the program up top. Here's the program. You have the carrier wave, and where you have the crest here, you're just going to increase the frequency, and where you have a trough, you're going to decrease the frequency. And that's how they modify FM waves to carry the program on it. So it's really one wave, but they've modified it in a way that your radio can pick it up and then play back to you the program.